What is gravity? As you watch this video, you can pick up the pencil in front of you and it falls back down to the ground as you let go. Excluding air resistance, you know it will accelerate at 9.81 meters per second squared, where little g is the gravitational field strength. But as you expand your reference frame outside your room, problems occur. A small triangle drawn on the surface of the Earth obeys Euclidean geometry because locally the ground is almost flat, but enlargement curves the edges and the sum of angles rises above 180 degrees. This is why aircraft take curved journeys to save fuel and time, because the shortest distance between 2 points on the surface of a sphere is not the straight line we would assume. The Great Circle is a spherical geodesic. Similarly, our view of gravity must change from room to Earth. Here's a nice analogy. From a young age we depict our local star, the Sun, like this, and it is very perceptive. The luminous power is constant, yet as the light propagates its surface area increases. The intensity decreases. As the surface area of a sphere is proportional to r squared, we deduce that the intensity of light follows an inverse square law of the radius. Gravitational fields are visualized using field lines, which point at right angles towards the gravitator's center of mass from all directions. Our field lines replace light rays in the analogy, and the inverse square law holds. Newton famously postulated this, along with direct proportion between little g and the mass of the gravitator. This produces the relation g is proportional to m over r squared. So now we have shown little g is not constant, but variable with radius. The proportionality constant is better known as big G, the universal gravitational constant. Through analogy and derivation, we have shown that the uniform field model of our room is only accurate for very small changes in r. Similarly, astronomers have found through observation of the cosmos that the universal law of gravitation starts to become inaccurate over larger systems. This was all because Kepler modelled very simple systems. Using the ULG and some elliptical geometry, he took the Sun, orbited the Earth around it, and the Moon around that. Huge differences in distances and masses allow this model to work well enough. We don't feel lighter during the day when the Sun is above us, and heavier at night when it's on the other side of the Earth, so its attraction in our everyday perspective is negligible. This illustrates how the Sun-Earth and Earth-Moon are two quasi-independent binary systems within the three-body system. However, mathematicians have probed the three-body situation where distances and masses are very similar, and one astonishing result is the possibility of a stable figure-of-eight system. Each body follows the other two around in a well-defined curve, and it is predicted that there should be at least one such system per galaxy. The n-body problem bothered astronomers for centuries. King Oscar II of Sweden famously suggested a prize for the first general construction of gravity between n bodies in the 1800s, and Poincaré notably deemed it impossible at the time. The situation too quickly rises in complexity as n increases above 2. A shortcut used by astronomers is called the star superapproximation. The idea is to condense the billions of stars in a galaxy to a single centre of mass and model any individual star's motion by a two-body orbit around it. However, comparison of the orbital speed curve from the star superapproximation and real data from telescopes is famously humbling. The issue is that the star soup is not static, but rather a dynamic system where individual two-body interactions kick and drag masses about, appearing much like Brownian motion in a gas. Observations of local galaxies show that they rotate way too fast for their size. Like a fragile record spun at thousands of RPM, we would expect them to shatter and spray their contents across the cosmos, but they are remarkably stable. And this is where the infamous theory of dark matter arises. We need some extra mass to account for the lack of decay in the rotation curve, an enormous amount of it. In fact, to keep the Milky Way stable, we would need roughly 7 times as much of this invisible stuff as the matter we can see. So why have we never detected it? The best model so far is the WIMP. By definition, they are hard to detect. You can't just spot a lump of them floating in outer space because they don't interact with photons or any other force carrier save the alleged graviton. Furthermore, since WIMPs are so massive, the Large Hadron Collider does not have a high enough energy to inspect them from collision data. An even graver assumption is in store, though. Current models of gravity cannot explain how the universe is so large so soon. Inflation theory loosely attempts to explain, with the similarly elusive inflaton responsible for accelerating matter after the Big Bang. But gravitation should have slowed this expansion, right? Well, redshift data indicates expansion continues aggressively, and dark energy, which allegedly accounts for around 70% of the universe, is attributed to fueling this. To the casual onlooker, this all seems incredibly science fiction, and it is. We started out with very reasonable developments in the theory of gravitation, from the uniform law to the inverse square one, and from there, inconsistencies led to wacky theories trying to explain them away. The dogma of dark matter is prevalent. Many scientists are convinced it is the solution, and are loath to pursue other options. Clearly, these other options involve overturning centuries of work, so the reluctance is understandable. Physics is incomplete, and this is what makes the pursuit or disproof of dark matter and energy such an exciting field at the moment. Thank you for listening.